So now we look at a different type of homogenization that's possible whenever you have a problem where the non-homogeneous term in the PDE and also in the boundary conditions, when these are all constant. So now these don't necessarily need to be uniform. I mean, in the PDE part, it can depend on x, that's fine. But it does not depend on t. So they're all constant. Now, in that case, when they're all constant, then as time goes to infinity in the long run, we expect this to tend to an equilibrium state. And the equation for the equilibrium state will be given by minus kuxx equals fx, because the ut part tends to 0. And the boundary conditions will roll over onto this equilibrium variable as well. And then this can easily be solved just by integrating. So we take minus kf and we integrate it a couple times, and each time we get a constant. So we first get a c1 and then we get a c2. So it'll look something like this. But the key point is that you can solve for u, and then you can define w to be u minus the equilibrium solution. And it will solve the system that looks like wt minus kwxx equals fx, equals 0 now. And WAT equals WBT equals 0. And then the initial condition changes to being WX0 equals GX minus UX. So we subtract out the equilibrium solution from the PDE and then also from the initial values. So now let's see. So now that we have that this thing is fully homogeneous right here, we can solve via separation of variables. And if you were wondering how these things came about, let's just look at WT minus KWXX with this substitution. So this is going to be UT minus KUXX minus capital UXX. So capital U sub t is equal to 0. So there's no term right there. And then this regroups as UT minus KUXX minus K capital UXX, which is going to give you fx minus fx, which is 0. All right, so that's the explanation for this part right here. For the explanation right here, let's just look at what happens at A. If I take W AT, this is going to be UAT minus UA, which is A minus A equals 0. So that's where that comes from as well. So the idea here, and the thing to keep in mind, is that if you subtract the equilibrium state then the system evolves just toward being identically 0. And so in some sort of made-up, makey-uppy, goofy symbols, in general, the state variable u, as time goes to infinity, it's going to tend to equilibrium. But because we're looking at a linear PDE here, we can also look at it as taking state variable minus the equilibrium solution, and then that's going to tend to 0. So this is directly analogous to when you were doing an ODE class and you found that your solution looked like some transient part plus some steady periodic part, and then as time increases, the transient part goes to 0 because that's what transient means, and you're just left basically seeing the steady periodic part. And in general, when that happens, the transient part comes from the intrinsic properties of the system, and the steady periodic part comes from the forcing function. And so that's exactly the same kind of thing that we're seeing right here. We're seeing that the solution is kind of, there's the equilibrium part of the solution, and then there's the transient part of the solution. And I guess I put these in the wrong place. Let me just fix that real quick. Okay. And then the transient part here, this is the solution to the homogeneous part, which again is the intrinsic kind of part, what's naturally in the system, including initial conditions. And then there's the equilibrium solution, and this is what comes from the forcing, what the boundary conditions are forced to be, and what the PDE, what the sources are. Oh, and when you read this section in the text, I recommend reading it as 429, where the idea is introduced, and then look at 431, for example.